Have you ever wondered what connects a diamond, a tree, the fuel in your car, and even the DNA inside your own cells? Well, there's a secret code, and its name is organic chemistry. Today, we're going to crack that code and explore the chemistry that builds our entire world.
And honestly, that's not even an exaggeration. Just think about it. The clothes you're wearing, the phone or screen you're watching this on, the very cells that make you, well, you, it's all built on the rules of organic chemistry. So this isn't just some textbook topic. It's literally the instruction manual for life.
All right, so here's our roadmap. First, we'll figure out what organic actually means in chemistry. Then, we'll meet the absolute superstar of the periodic table, carbon, and see how it builds the simplest family of molecules. After that, we'll learn how to give those molecules some personality before we see them in action in stuff we use every single day.
So, what is the big deal with organic chemistry? I mean, why does it get its own special branch of science? It all boils down to one huge question. At a chemical level, what's the line in the sand that separates living things from non-living things?
Well, it really comes down to three key differences. First up, where they come from. Organic compounds, historically, were thought to come from living or once living things. Inorganic compounds, they're from non-living stuff, like rocks and minerals. Second, the main character. Organic chemistry is almost entirely the story of one element, carbon. And third, it's about how they're put together. Organic compounds are all about sharing electrons. We call that covalent bonding. Think of it like a team working together. Inorganic compounds often involve one atom giving an electron to another, an electrovalent bond. This one difference in bonding changes absolutely everything.
And that brings us to the undisputed MVP of the elements, carbon. Seriously, what gives this one atom the ability to form the backbone of millions, and I mean millions of different compounds? It all comes down to two incredible superpowers. Okay, superpower number one is called tetravalency. Tetra just means four. You see, carbon has 4 electrons in its outer shell. Now, it's in a tricky spot. It takes way too much energy to either gain or lose 4 electrons. So carbon does something genius. It shares. This means it can form 4 incredibly strong, stable connections at once, making it the ultimate connector, the social butterfly of the atomic world.
Carbon's second superpower is catenation, and this one is really special. It's just a fancy word for carbon's amazing ability to link up with itself, over and over and over again. Carbon atoms can hold hands with other carbon atoms to form these incredibly long, stable chains, complex branches, and even perfect rings. This is the secret to building the gigantic molecular skeletons that make life's complexity possible.
And here's what that looks like. Thanks to catenation, carbon can form simple, straight chains, just one after the other. Or it can get more creative and form branch structures, kind of like the branches on a tree. Or it can even loop all the way back around on itself to form super stable rings. These 3 shapes, chains, branches, and rings, are basically the Lego bricks that build the entire world of organic chemistry.
So we've got carbon, our master builder with all its superpowers. What happens when we pair it up with the simplest atom of them all, hydrogen? Well, you get the most fundamental family of all organic compounds, the hydrocarbons.
Now, this family has 3 main branches, and it all depends on the kind of handshake the carbon atoms are doing. If they're sharing just one pair of electrons, a single bond, we call it an alkane. If they share 2 pairs, a double bond, it's an alkene. And if they share 3 pairs for a super strong triple bond, it's an alkene. Each one even has its own neat little formula, so we can predict their structures.
And this leads us to this really elegant idea called a homologous series. Think of it like a family where all the siblings look and act pretty much the same because they have the same core structure. Every member of the alkane family, for example, reacts in similar ways. And to get from one sibling to the next one in line, you just add 1 carbon and 2 hydrogens. It's this beautiful, predictable pattern that brings order to the chaos of millions of compounds.
So if there are millions of these things, how on earth do we name them all without going crazy? We use a universal naming system that's actually pretty simple. It's like a 3-step recipe. First, find the longest continuous chain of carbons. That gives you the root of the name. Second, look at the bonds, single, double, or triple, to get the ending. And third, just name and locate any branches that might be hanging off the side. It's a logical system that lets us name almost anything.
Okay, but let's be real. A world with just carbon and hydrogen would be kind of boring. The real magic, the real chemistry, happens when we start swapping out some of those hydrogens for other, more interesting groups of atoms. These are called functional groups, and they're what give a molecule its unique personality.
A functional group is basically the action-packed part of the molecule. It's the site where all the chemical reactions happen. So if you stick an OH group on a molecule, it becomes an alcohol. Slap on a -COOH group, and now you have a carboxylic acid, which often tastes sour. These small additions completely change the molecule's behavior.
Let's just take a quick example. Take ethane. It's a simple hydrocarbon gas, and it does not mix with water at all. But if you just swap one single hydrogen atom for an OH group, you suddenly have ethanol. It's not a gas anymore, it's a liquid, and now it mixes perfectly with water. See? That's the incredible power of a functional group. One small change, a totally new molecule.
All right, let's bring all this theory back down to Earth. Let's look at how these ideas play out in two molecules you have absolutely come across before. Ethanol, which is the alcohol in drinks, and acetic acid, the stuff that makes vinegar sour.
So on one side we have ethanol, defined by that OH functional group, which makes it an alcohol, and on the other side we've got acetic acid with its COOH group, which makes it a carboxylic acid. So, ethanol. It's a volatile, flammable liquid that, as we saw, loves to dissolve in water. On an industrial scale, it's made by adding water to another hydrocarbon called ethene. And we use it everywhere, from alcoholic beverages to solvents in perfumes and paints to the antiseptic you use to clean a scrape.
And when we talk about beverages, the concentration of that ethanol makes all the difference. A beer might have around 4% ethanol. A glass of wine is closer to 11%. And then spirits like whiskey can jump all the way up to 40% or even higher. It's the exact same molecule in all of them, just in very different amounts.
And now, for acetic acid, the molecule that gives vinegar that sharp, tangy kick. Here's a cool fact. If you get pure acetic acid and make it cold enough, it actually freezes into these clear crystals that look like ice. That's why it's sometimes called glacial acetic acid. Of course, we know it best as vinegar, which is just a 4–5% solution in water, and it's a great food preservative.
So here's where it gets really cool. What do you think happens when our two feature molecules, ethanol and acetic acid, get together? They undergo this beautiful reaction called esterification. The alcohol and the carboxylic acid react, and they create a totally new kind of compound called an ester, plus a little bit of water on the side.
And here is the magic. That brand new ester they just created, it smells amazing. We're talking sweet, fruity aromas. Esters are basically nature's perfumes and flavorings. They're the molecules that give things like bananas, pineapples, and flowers their distinct, wonderful smells. So many of the best scents and flavors we know are all thanks to this one simple reaction.
So we've seen how carbon's unique talent for building complex structures is the foundation for all life as we know it. It really leaves you with a wild thought, doesn't it? What if another element had these same superpowers? Like silicon, for instance. It's right below carbon on the periodic table. What would a silicon-based world or silicon-based life even look like? It's a question that really pushes the limits of chemistry and our imagination. Thanks for digging into this with me.